So here I'm going to talk about our digital infrastructure and data pipeline showcase in our GlasDigital project. So first, complete short introductions. So nowadays, the glass melting is very cost, energy, and time intensive due to a low degree of automation. So in our project, we aim to build an ontology-based digital infrastructure for data-driven, high-throughput glass. And here you see we have robots implemented in BOM, which is a robotic uncontrolled glass melting system. And here are some challenges we aim to solve. So first is the inline sensor technology for the process monitoring. And then also the high throughput glass analysis tools for process optimizations. And then the glass ontology and database for the entire value chain. And the end is machine learning algorithms for glass design improvements. And to do that, we have to have multiple collaborations between different universities and institutes. So of course, the robotic melting system in BOM, and also inline sensor technologies, and also analytics. And also we have image analysis, mainly for did in TU cluster, and also inline sensor. And then we also have property modeling and system control in Fraunhofer Institute for CK research. And also we have an external collaborate with data mining with Universität Würzburg. And then the process optimization with digital twin and workflow doing in another group in Jena. And in our group, I focus on glass ontology in the database and interfaces. And my colleague is doing the machine learning tools. In the end, everything will be integrated. And this is a joint project with also industrial leads. And here you see the robotic melting system control app. So in here you see here is a software which controls the recipe of the glass, of all the raw materials, the mole percent. And then once the information, the input is sent to the robot, and then it will start to work, and then everything will be automated, processed, and measured. And then all the individual inputs of reference process parameters and also time series information will be stored automatically in JSON format. And then further this JSON format raw data will be converted and then into the triple stores. And here you see the inline sensorics. So we have sensors for in situ glass forming. So with the temperature raises, you see here the images from raw materials and to start reaction and then to gas release. So the recording of these melting kinetics allows optimization for the melting process in terms of time and energy for different raw materials. And then furthermore, this will be used for machine learning training data sets. And then we also have sensors for viscosity and casting. And here you see the image of the casting and the flow rate control for maximum yield. And those image data will be used to train the model RaceNet 34, which is a neural network in Python. And here you see a software in situ monitoring the melting process. So in here, it can detect the melt status in granules or foaming or glass melts. And then we can use this tool to better understand the melting kinetics and then optimize the melting process and batch to melt time. And this tool is developed in TU CloudStack. And we also have high throughput analysis. So here you see the image of homogeneity and stress distribution, and also Raman spectroscopy and thermal properties using the differential scanning calorimetry. And the other properties will be measured is the density and the chemical composition and other mechanical stability. And here you see a prototype to facilitate the data input process. So in here, I made a prototype for different methods. And then in here, you see a lot of input fields. So the users can directly type the values and then providing the data source and other information or raw data, and then upload to the server. So currently, these are the main measurements we focus on, and maybe some more in the future. And then this is a prototype. So once the ontology is connected, it's ready to use and automatically convert the raw data into a triple store. And this GUI is connected with the ontodocker. So here we use the API key to authorize the users and then to gain access to the database. And here comes to digital twin. Here we have finite element simulations using the software console. And here we're simulating two types of behavior, the casting process and the viscosity control. And here you see some images of the behavior. And here we are using this kind of digital twin to optimize the whole melting process. And here's the glass ontology based on PMD Core Ontology version 1. So here you see a partial graph here. So the object here we focused is, of course, the glass. And here we have the process for the glass and also the process parameters for the glass. And then here you see the manufacture process. And inside the manufacture process contains the batch process, the melting process, and followed by the cooling process, or an optional process, the crystallization process, which is what we don't want it. And here the input object is the raw materials. Here you see some oxides in here, and the different methods inside the analysis process. And those analysis process will measure the property of glass, and then to get the material property, density, viscosity, or elastic constant, and even more. So we don't actually have so many properties measured during the experimental, but we have a lot of different properties from open source database. And here, the process parameters, for example, the pre-melt heating rate, melt heating rate, and cooling rate, and 20 more properties, 20 more process parameters are stored in a JSON file. And then later we will use ontodocker to map these data and store in a triple store. And then we can track to each steps of the melting process to know the specific process parameters for each glass ID or different raw materials. And here's an outlook for the digital infrastructure and data pipeline. So here, the whole application is within Docker, installed in the server in Vienna. And here you see we're using an open source identity management software Keycloak to protect the application from unauthorized users. So once the user is authorized and they can access to our database, either in the web GUI or using the desktop GUI. So here the connections between the GUI and the backend is using the API key generated inside the ontodocker app. So you could find this fast ontodocker app in this PMD GitLab. So this is a rebuilt version of the initial released ontodocker and modified according to the requirement and the situation in GlasDigital. And here the triple store we choose is the project in Vienna currently. And I know there are some project members, they're using BlazeGraph or GraphDB. So these two triple store will be supported in the future in fast ontodocker. And here you see the data source. So we have the data source from the robot in JSON format and the open source database data source in CSV format and the patterns in PDF format and image analysis in image format or even in video format. And then for patterns, this will be extracted using the data pattern extraction tool and converted into JSON and then further mapped to the glass ontology. And then two major data sources are, of course, the melting process and the open source database. So these two will be more focused and wrapped and mapped with the ontology. And then as for the image analysis part, these will be stored in the local file system and providing the metadata stored in JSON and then stored in the triple store. So for later on, we will query those metadata of the image analysis and then can get the raw images directly from the file system. And this is, of course, protected by the ontodocker app. So here's come to the live demonstration of this knowledge base. So here you see the login page of our knowledge base. So here I'm using another account. So as you can see, the fast ontodocker is capable of serving multiple projects. So here you see the GlasDigital project and this project I'm currently working on, and also internal project in our group. So here you see different material classes. This is glass, and this is antimicrobial biomaterials, and this is organic compounds, having also solvents and polymers. So here comes to the showcase of the GlasDigital. So here you see a welcome page. And one of the advantages of using the fast ontodocker is that you could have an API document automated automatically generated. So you can directly try out some of the APIs and largely accelerate the development time. And if you want to use the desktop version of the GUI, you can use the API key in here. And by typing in this API key in the GUI, and you can also grant access to the database. So here I first show you the open source database inside Glass. So here I create a simple UI for the input of the oxide and the properties measured. So in here, for example, I choose this MBS graphs. And of course, if you want to query specific oxide, you can directly type and you can find the oxide you want. And in here, as a demonstration, I could use the density and all the mechanical property here and directly make the query. And this UI will have a script to generate the template of SPARQL query directly. And here you will see the result. It's so fast because by default, I use a cache system, an in-memory cache system in the backend. So if the more users are using, the more faster you will get the results. So if you here see the glass compositions and the total mole percents, so you can also query it or filter it by some conditions. So you can say, I want silicon oxide greater than 70. And here you will get the results from the filter. And then you will see the density and Poisson's ratio, shear modulus, and Young's modulus. And here you will see the reference because this is the largest glass database. And this data set is not complete and inconsistent. So it's very important to provide the reference of the source. And then we could plot a ternary plot to get a distribution of the glass compositions. And also do a scatter plot. Like this, or change the X and Y properties. So you will see some correlations and good visualization. And also a histogram plot showing you the distributions. And then we have SPARQL endpoints, 3 of them. So the first is the query endpoint and update point endpoint and upload endpoints. So for advanced users, they can use the code editor directly in here. But of course, for normal peoples who doesn't understand the SPARQL language or the underground glass ontology or even PMD Core Ontology, they're welcome to directly use the query UI to quickly get the results they want. Or for the advanced users, they can make a specific queries directly in here. In here, they didn't match the filter. I need to close it. Clear. Oh. Okay. And rerun again. Sorry. In here, I use a cache system. So maybe last time I made a query that doesn't find a result. So here is some typos in here. And as for the bound data sets, so currently we focus on the NABS graph system and also MBS graph system and NCS graph system. But we don't have too much data on this. So the majority is NABS and NBS. And as for the properties, I'm working on it to bring in here. So it will come soon. So in here, NBS graph system. So again, a cage system directly return the result very quickly. And you will see here all the glass we melted according to the glass ID. So the first column is fixed to improve the user experience, to check all the processing parameters in here. And also if you want to download the raw data, you can also create a download file. And here you will find the directly matched JSON raw file. And you can even export to CSV or in Excel worksheets, or copy the whole data. And again, the ternary plot and the time series plot, which is useful for tracking down the mistake or some potential stop time for the melting or cooling process. So here I'm showing you an example of the time series plot for cooling temperature. And it will automatically mark the maximum temperature in here. And you can move your mouse to check all the values. And here you can choose all the glass IDs to check for each glass melting process and cooling process. And we have glass prediction features, which is a machine learning model implemented in the backend, all written in Python. So here you will see we have GPR models or neural network model or random forest or supporting factor machine. And as for a property, we currently have 4 properties. And here, as demonstration, I use a GPR and density. And you can query one by one. For example, like this. And you can render in type, and it will show you some warning message. So just in case the sum of more percent is greater than 100%, so you know you should reduce the values. And here you will see the model you use and the formula and the total more percent and the property and the value with the standard deviation. Or you can use a built-in functions to predict the continuous or batch predictions for a certain range and certain steps. We are currently working on these to make it more user-friendly and more flexible, so you can change the numbers in here to have a customized machine learning graph. So for example, in here, I make batch predictions for these functions, and all results are kept in the table. And then you see here a continuous error bars plot from 20 to 74 more percent of silicon oxides. And you will see the trend in here. And furthermore, this machine learning tool, the batch function, will be integrated into these two databases to provide the first insight about the potential properties you want to make. And currently, these machine learning tools are trained according to the class compositions in here, and also up initial descriptors from ND simulations, and also as the experimental result, which is the process parameters, but to further improve the results in here. And we also have a pattern extraction tool, which is collaborate with Wurzburg. So we have two servers, one in Würzburg and one in Vienna. So this is also a Docker application. So in here, I can load the gas patterns. So here you see a US pattern, and here is the extraction result. As you see here, the extraction is not always perfect. So that's why this table is editable. So you can edit the cells in here to have it corrected. And also navigate to the page contains the table in here. So enlarge it. So you see here, table 1 is extracted automatically. And here I noticed there is some errors in here. So one row is missing in here. So what I can do is just copy this column and replace and type a new one. So in here, the table is fixed. And of course, there are some more to be fixed. But anyway, these will facilitate the speed of extraction, is additional knowledge from the pattern to provide more data source. And then in the end, there is a save function. You can save it and export it to a worksheet with different tab contents to the different tables. And you can also remove the row or remove columns if the extraction is not good. And also you could choose different sources from the link here. And also choose two different servers. So they have the latest development version, and we have the stable version. And if one of them is failed, we can always switch to different servers. And here you see some link of the documentation and visualization using the web file. And here you will see all the nodes in the Glass ontologies. So currently this is created based on PMD Core Ontology version 1. And I'm working on it to migrate it to version 2. And here we have a GitHub page in the PMD application ontology. And as I said, this fast ontodocker is capable of serving multiple projects. So this is fulfilled by using the keycloak, the role-based control. So because this account contains the role of multiple projects, so in here you will see a drop-down list of different projects. So I'm not going to show it here, but to mention about the ability of switching to different projects using one account. And then for the data pipeline is not released yet for the project member, but only the main users. So here I'm going to switch accounts. And again, this account can see all the projects. So in here, by default, I hide some data sets from normal users. So only admin can have access to a specific data set. And also only admin users can have access to the triple store server. So in here, I could go to the page YANA. So you see here the main UI of the page YANA Fuzeki. And this is user controls. So you have to be the main users to have access to it. And in here, you can create a data set. For example, taste. And data set name is created. And in here, since the query UI is specially made for each data set. So in here, the taste data set is not supported. So if there is a new specific data sources, then someone have to implement the corresponding query UI to do the SPARQL mapping. And for those that doesn't have the query UI, they can always use the code editor in here to make different queries with different tabs and update the partial data, or upload the ontology file. So in here, I can upload with turtle file or RDF file. And for the data pipeline here, so this data pipeline converts raw data. So the raw map is Excel file, CSV, and JSON into semantic lake data. So as a demonstration, I show here only JSON. And so first, this is a file uploader. And then in the backend, we have a canonicator, which is a wrapper script to wrap the raw data into a standardized form of data in JSON format. And then a mapper, which maps the canonical JSON into RDF triples in turtle format. And as an admin, I can download and write to the triple store. And for project members, it's under review and not for guest access. So for example, I can browse here for the robot melting raw JSON file. So it's capable of uploading multiple files. And then you see here, all the files are loaded and wait for uploads. And you can always start. And the result was showing here, and you can download the processed file. and the result will be in turtle format with the corresponding file name. And then once you upload it, and you can go back to the data set here and then check for the results. And as this demo doesn't really rise to the triple store, so this is still an ongoing features to be implemented and to get more user feedback and provide a more user-friendly UI to facilitate the data pipeline. And also in the future, there will be a measurement UI. We already have a software, but in the end, we will also have a web version because it's more easily to implement and dynamically change the UI or the ontology. And then once the layout and the functionality are fixed and confirmed, we will release a stable version of the software. And then here's the summary. So the data acquisitions, including the data from the automated processing and the literatures like patents and open source database, the SciGlass database, and also the image from the inline sensors and the property simulations. And as for data structuring, we are using PMD Core Ontology to build our GLAS ontology. And then the raw data CSV or JSON is converted to triples using the Python library RDF-lib on the backend. In the backend is the fast ontodocker, which provides front-end query UI and role-based user access control and management using an open source solution Keycode. And with that, we can use the API key generated in the ontodocker to have a Windows or Mac or Ubuntu-based software, all written in Python. And also there's a triple store integration currently on the Futaki, but there will be BlazeGraph and GlassDB. And table with copy support search and filter functions and plot visualization functions by using an open source plot library and easy to expand. So in the showcase, I show you the machine learning models used to predict the glass properties, and image analysis part I haven't shown you yet, but we are planning to implement the in situ image analysis for the glass forming also in the web UI. And the pattern instructions. And as I said, this ontodocker is designed to make multiple types of materials. So it's very suitable. And here's the contact informations. So you can find this fast ontodocker, which is a rebuilt version of the first initial ontodocker. And also, you can find it in GitHub, while I haven't released it to the GitHub, but you can find the latest release version in GitLab. And you can find me or contact me by email. And here's our GlasDigital team, the GlasDigital team members, and the collaboration in the pattern extractions. And okay, thank you very much.